Good afternoon. I am on a bit of a hiatus today, so I'm a little bit bored, extremely bored, and I'm going to show you how to write a smart contract in Python on Algorand that allows you to get the price of Algorand on chain. And we're going to be writing a second method that also allows you to input a target USDC amount, and it will output the equivalent in Algorand. So for example, if I input $1,000 USDC, it will give me the equivalent amount in Algorand for that price. Um, if you're a bit more familiar with how things work on Algorand, or if you're already a developer and you don't really want to watch the whole thing, I can quickly explain what it does. So essentially, it gets the local state of the USDC pool address against the Tinyman router application, and we're going to be using testnet because we're not crazy and we don't want to waste our precious algo now that we have staking incentives live. Um, so the local states of the pool address against the Tinyman router application, there are two local state keys in particular that we're interested in. That's going to be the asset 1 reserves, which is going to be the USDC amount in the pool, and asset 2 reserves, which is going to be the algo amount in the pool. So the first method where we just get the price of Algorand, you basically just scale the amount of USDC divided by the amount of algo. There you go. You have the price of Algorand. For the second method, you input the target USDC amount, you scale it a little bit again, and then you divide by the scaled Algorand price from the initial method that I just mentioned. So the reason we scale is because sometimes, one number is bigger than the other. Um, Pretty much like all blockchains, they only allow floor division. You can't do floating point division. Decimals don't exist. So you scale just in case one reserve is larger than the other. Because, for example, if I do 2 divided by 4, that would be 0.5, right? But on blockchain, when you do 2 divided by 4, you get 0, right? Because there's no such thing as a floating point decimal. So what we use are scaling factors. And you're going to see that now. I guess I'll start typing away. So from AlgoPy, import arc4 contract, and we're also going to need ABI methods. We're going to need a few other things too. Let me think here. Accounts, application, and UN64 should be sufficient for now. So we're going to define our contract as a class. So class get algo price contract. Why not? Pass in the arc4 contract object, and we're going to initialize, pass in self, type annotation, return none, and we're going to define two global states. You don't really need to put them in global state. You can actually just program it into the actual method. But I just like using global states and I don't like doing this. Just passing on initialization. I feel like, it should be used. So the pool address. If you're not sure how to get the pool address, it's basically like this. So for example, here I have the pool logic sig template, which is provided by Tinyman, and this is where all pool contracts originate from. Um, but essentially what it does here is you pass in the first asset and then you pass in the second asset. So USDC and Algo, these are the asset IDs. Algo doesn't really have an asset ID, so by default we use 0. And then this is the application ID for the Tinyman router on testnet. We also have the mainnet one, but again, we're not going to be using mainnet. Arbitrary address, you actually don't need this. I don't know why this is here. But you get the logic sig by passing in the application ID of the Tinyman router, asset A ID, and asset B ID. And what it does is it takes the program template for the smart contract and it encodes or kind of squeezes in, replaces bytes in certain positions using this information that we're passing in. So for example, from byte index 3 to 11, we replace those with the validator app ID or the Tinyman router. Um, Bytes index 11 to 19, we replace that with asset 1. And bytes 19 to 27, we replace that with asset ID 2. And then you get this logic sig account of this program, which is going to be in bytes. We decode it here. And this logic sig account has a method here called address, and it just returns the address of the logicsig account. And then this is going to be the pool address. And I've already obtained the pool address right here. We could run this code and get the same output right now. So yeah, UDFW, same as what I have here. And so this is going to be the first global state. We'll call it the USDC pool address. And this is going to be an account type, and we'll just pass that in as a string. And then the second thing is going to be the tinyman router, and we'll define this as an application. And this is going to be an integer. I'll just grab this right here. Perfect. So now we have our global states, and we're going to create our first method, ABI method, and this is going to be called getScaledAlgo price, and we're going to pass in self, return none, no arguments needed. And what we do here is we're going to define the USDC reserve, and we're going to need the op module here as op.applocal getX UN64, because the local state we're trying to access outside of our smart contract is going to be a UN64 value type. And it's going to need three arguments. So the first argument, as you see here, A, is going to be the account, which is the USDC pool address. The second argument is going to be the tinyman router application, the application that holds this local state. It's going to be tinyman router. And the third argument is going to be the bytes format of the local state key, which is asset1 reserves, plural. When you get the local state, it's going to return a tuple. And this tuple will be an integer and a boolean. If the local state exists, it will return the integer value and the boolean true. If it does not exist, it will return 0 and false. So we want the integer value directly, so we'll just access the value at the 0th index or first position. For the algo reserve, we'll do exactly the same thing. We'll just change the variable name here to algo reserve, and over here we'll change this to 2. And now what we want to do is define a scale factor, which I'm going to use 1 million. You can adjust this as you'd like, but this is what I prefer. It gives me a nice rounded four integer long number, so in the thousands. And you can just easily throw in the decimal point between those two numbers. For example, if I get 3570, uh, it'll just be 35.70. So to get the scaled algo price, you're just going to multiply the USDC reserve by the scale factor and use floor division with the algo reserve. And that's it. Now you can just return the scaled algo price. If you want to be fancy, you can even return this directly and not create a variable. So fancy. Oh my goodness. All right. Now writing the method for inputting a target USDC amount and getting an output for the equivalent in Algorand. So I'm going to write a second method, get target USDC amounts in algo. Wonderful. And the argument is going to be present here. I'm just going to call it target USDC. This is going to be a UN64 type annotation. We're going to return a UN64, which we should do here as well. Sorry about that. And over here, it's a very similar process, except we don't have to do this step here. We can just call that. If we copy and paste this and make it a subroutine, and import subroutine. So subroutine is something that executes like a function in the contract instead of something that you can call. I don't know if I'm explaining that enough, but basically you can't call this function. This is something you call will go and fetch the return value for. So I would call the get target USDC amount an algo method with an application call. And then for me to get the scaled algo price, I just call this function internally. So it would be like so, just like that. So now that I have the scaled algo price, I just need to get the target USDC amount. So what I'm going to do is I'm going to use another scale factor. Here I'm going to use 10 million, and the amount of algo will be target USDC, or let's say amounts in algo is going to be target USDC times scaled algo price, excuse me, times scale factor divided by the scaled algo price. And then we can return amounts in algo. And that's pretty much it for the contract. I guess I'll show you how to call this. This looks wonderful. So in the terminal here, let me just make sure I save this. When you see this little white dot here, it means it's not saved. So let's file, save all. And we're going to type algokit compile pi and then the name of your contract file. And hopefully we don't have any errors, but luckily the compiler is wonderful. So let's see here. Returning any function declared to return UN64. So that's a problem. Name already defined. We cannot have functions that are called the same thing. So I'm going to call this call get scaled algo price because I want to show you two separate examples. So I want to show you how the price comes out first and then this function separately, these two. Perfect. So that fixed the problem. And now we're going to create a new file here. I'm going to call it, I like prefixing with an index so I know in what order to go in the future. But this is going to be one underscore deploy contract dot py. And we're going to import algod client as well as the from algokit utils, we're going to import the application client. And we'll define the app client here and work our way backwards with defining things. So the first thing we need is the algod client. And we're going to define an algod token. We're just going to use Nodely. And the algod, I usually use server, but we're going to use address because that's more proper. And the token's empty for Nodely, but if you go over here, so you go to nodely.io, click quick start, and down here you'll see the indexer and algod endpoints for mainnet, testnet, betanet, fnet. There's more. You probably won't look at more. So I'm going to get the testnet algod API, which is right here. And we're just going to bring that back to our code and input this here. And for algod client, we just construct this here by passing in the token and address. And that's the algod client. Next up, we're going to need the app spec. So the app spec is just going to be this arc32.json here. So app spec is equal to, and we need pathlib for this. So from pathlib import path. And this is going to be path file dot parent and then the name of your arc32. Wonderful. Next up, we need the app ID, which we can define as 0, but by default it'll be 0. The app does not exist yet. Signer. This is an object that allows you to sign, import account transaction signer. So you can sign transactions like this application creation that we're about to do. So the account transaction signer, we're going to need to generate an account actually. So generate account.py, and this is the easiest thing to do in the world. So private key address equal to generate account. We'll just print the private key and address here. And I'm going to create a .env just so it's a little bit more proper. So we have here our private key, create a .env right here. Just call it pk and pass in that string. And then same thing for the address, but I like using the address from private key method from the accounts library. So now that we have an account, we don't need this anymore. Sorry about the beep. So signer is equal to count transaction signer. We need that private key. So private key is equal to os.getEnv, and I named it pk, and we're gonna need os from.env import load.env. I don't really need this, but some people do, so that I can load the .env in the same directory. And signer, pass in private key, and that's going to be our third argument here. Up next, we have sender, just the address. So address is equal to, and we'll need that from the account library. You can also just read it from the env if you don't want to be fancy. It's fine. Sender is address. Next up, we have suggested params. And this we can get from our Algorand client that we just created. Perfect. And we want 1R in params. And that should be it. Let's double check. Yeah, we're not going to use template values. So this is good. So we're just going to use app client dot deploy. You can spell this right. Wonderful. App ID. We just need the app ID. And app ID equals, and we're just gonna, we can use set key. Why not? So set key dot env path. Key to sets will be app ID, and value to set will be the string version of the app ID. And we'll print the app ID as well, even though it'll be in the end. And we should be able to run this, except we do need some testnet Algorand. Oh, bank. Let me just Google it. So there's a dispenser for Algorand on testnet, and I just go over here, bank.testnet.algorand.network. Status code 200, success, wonderful. So we have our Algorand now in that account, and we should be able to deploy, assuming no errors. No creator provided. We need a creator parameter, which is hidden. I don't know why it's hidden when you want to deploy, but existing deployments. We're also going to need an indexer client when you're deploying. So up here, I'll just pass it in here. Indexer token, indexer address, and indexer client. And we can do this similar to how we got the Algorand client. Perfect. And the indexer address we can also get from Nodely. So it's going to be right next to the Algorand testnet address. Punch that in here. And pass in the indexer client. And we should be good now. Perfect. So you see the app ID prints here, 1046 last four, and then you also see it in our .env here. So now let's interact with the contract. So let's just test out the getAlgo price, which is the first method that we wrote. We're not going to need the client anymore. We're not going to set any keys. Oh, just remove set key. Still need to load from the .env. And everything else should be good here. Remove this and remove creator, remove set key. We don't need to deploy. And we're also going to need an atomic transaction composer, which we can actually just get right here. And we won't need a transaction with signer object. So this is good. So we're going to do app client.compose call and pass in the atomic transaction composer, which we need to define here. Create an instance and call ABI method. So this is just the name of the method as a string. Call get scaled algo price. And we're just going to punch that in here. Doesn't take any arguments. So now we can just results is equal to atc.execute algod client. Wait rounds, I always do 2. And then the ABI results is equal to results. Actually, we're going to use an iterator object. So results.ABI results I for I in dot return value for I in range in length uh, results.ABI results. It should be good. And then if we want the transaction IDs, we won't really need them. In fact, we can even simulate. We don't need to be wasting precious algo. Algo SDK v2 client models import dot simulate request import simulate request. And what we'll do here, sim request is equal to, I'll do this after the compose call, atc simulate request object, and transaction group is going to be atc dot build group. And then instead of atc.execute, we'll use atc.simulate, and this is going to need the client and the request, the simulate request object. And this should be good. And then transaction IDs, I forgot about almost. For I in range length results dot transaction IDs. And we'll print the ABI results. Let's use an F string. And then the transaction IDs. All right, let's give this a spin. We need the app ID. So I'm just going to bring that in right here. os.getEnv app ID. This needs to be an integer. And then define this in here. And we should be good. So let's give it a spin. See what goes wrong. Perfect. So ABI results none. Let's see why that occurred. Dun, 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 dun. I think that is very weird. Compose call ABI method. There should be, I'm going to print results. See what happens here. It might be possible that it's failing. Results dot simulate response. I don't see why it would fail. Oh, we're missing our account reference and application reference. So in here, we're going to, what's going on here? Missing the comma. We're going to pass in an accounts list and the pool address we have here. And then we're also going to need the TinyMan router application reference. I'm going to grab right here. Perfect. Foreign apps, also a list. And just copy and paste these in here. Won't need the simulate response. I assume this will work this time. Perfect. So the current algo price is 172,33619. And if we go to the TinyMan resources, what is going on here? Oh, documentation. Search for testnet, and we'll get access to their testnet interface. And if you input here one algo, you'll see it's $18.26. And this is going to be a bit lower. But let's just do this here. We're gonna divide, instead of doing this iterator object, or actually, I just do this algo scaled, algo price, ABI results, 0, divided by, and we'll use a floating point division, 17, so 1, 2, 3, 4, 5, 6. Yeah, this is the scaling factor. And we should probably like this. Perfect. So you get 17.23. And I'm not entirely sure why the price is somewhat different on testnet. I would assume that there will be some fees involved, price impact, because if you type in, let's say 10,000, you'll see this quickly strays from the 1 to 18 ratio here. Yeah. So that's a 73.33% price impact. So it's a little off on testnet, but if you did this on mainnet, you'd find that it's relatively close to the actual price. So going back here, we're now going to write our second call, get target USDC amounts in algo super long. And we're going to simply input an argument, which is going to be called target underscore USDC, the parameter. And we're just going to copy and paste this ABI method name. So over here, we're going to copy and paste. And what was it already? Target USDC. We're going to create another parameter here. And let's just say 1000 algo. Okay. And that's pretty much it. We can now simulate again. The scaled algo price is not going to be divided by a million anymore. It's not even going to be the scaled algo price. It's going to be the Algorand amounts of USDC. API results, 0th index, first position. And we can even state here USDC amount is equal to 1000. And if we run this, we get 580, which is basically, we need to divide that by, I believe, by 10, which we actually should have done 100 million for something more accurate, but that's fine. So here we're going to divide this by 10. We'll use floor division. And if I pull out my handy dandy calculator here, and we times or multiply 58 by the algo price, which we'll get again here, 17.233619. 58 times 17.233619. You'll see we get very close to $1,000. So $1,000 USDC on testnet is approximately 58 algo. And like I said, I would adjust this scaling factor to be 100 million. So that's you can, actually, this doesn't matter. I would do this, but then you only get a 58, and you never know if you're going to get 58.5 or 6. That might make a big difference one day. And the scaling factor is used because there is a chance that the USDC reserve is less than the algo reserve. So I believe I mentioned this earlier, but if I didn't, I'll quickly explain again. So on AVM, on most blockchains, actually, when you are working with numbers and division, there is no such thing as a decimal. you usually need to scale because you are restricted to floating point division most of the time. But this is pretty much it. And oh, if you divide a smaller number by a larger number, the output will be zero. So we don't want a zero, right? So we scale. And similar situation here. If I ask for, let's say here, if I ask for $1 million in USDC and divided by the scaled algo price, let's say by chance the scaled algo price is still smaller, is larger than the target USDC amount, we are now going to get zero where we shouldn't. So we use scaling factors to be safe. This also increases precision since you don't have access to decimals. But that's pretty much it. Thanks for watching. Thanks for keeping me busy. I'm going to find something else to do and upload this to, I'll put this on GitHub and then I'll tweet it. Why not? I'll tweet this out. And I'm going to go check on my node too. Staking incentives. Absolutely amazing. All right, guys. Take care. Enjoy your weekend. Happy Friday. Almost time to start partying. Yeah. Bye bye.